Dr. Ranjit, sir?
Yes, sir.
Okay, okay. Thank you, sir. Thank you, sir.
Thank you, sir.
Professor Jayalakshmi ma'am.
Sir, good evening, sir.
Dr.
Sir?
Kala.
Yes.
Dr. Kalavati
Yes,
ma'am.
sir.
Okay.
Yes,
Thank you,
sir.
madam. Okay, madam. Professor Jayalakshmi madam.
She'll join later, sir.
Okay. Professor Dhananjayan sir.
Yes, sir.
Okay. Thank you. Dr. Kalavati ma'am, please ஒரு 2 minutes wait பண்ணுங்க.
Okay, sir.
Dr. Kalavati ma'am, shall we start, ma'am?
Yes, sir.
Okay, we can start.
Good evening to all. Good evening to all the participants. On behalf of Rajpalim Raju's College, Department of Physics, I welcome all the participants for today's program, International Online Faculty Development Program on current scenario in advanced material research and technology. Today's chief guest is Dr. Ranjit Kumar Raju. I invite Dhananjayan sir to deliver the introduction.
A very good evening to one and all. It's my pleasure to invite our today's chief guest for this session, Dr. Ranjit Kumar, postdoc fellow, Department of Chemical Engineering, Inha University, South Korea. He did his PhD in Kalasalingam University. He has published more than 12 research papers in the field of supercapacitors, battery electrodes, electrochemical sensors, and the energy storage devices with a maximum impact factor of 6.58. He has secured a best poster presentation award for international poster presentation competition organized by a group of 4 countries, India, Bangladesh, Sri Lanka, Thailand, in the year 2020. He also secured a best oral presentation for international virtual conference on recent trends in energy materials in the year 2020, organized by Alagappa University. On behalf of our department, we welcome you, sir. Thank you.
Thank you, sir. Can I share my screen, sir?
Yes, sir.
I would like to thank Dr. Raja, sir, for inviting me to deliver my research work in the area of energy storage material. Thank you very much, sir. Today, I'm going to talk about Facile synthesis and fabrication of carbon material for energy storage applications. In my presentations contains the opportunities in Korea, especially for master and PhD students, and I would like to give an introduction about energy storage and conversion devices, and a small introduction about carbon material and supercapacitor. And my research work is based on carbon nanotube and graphitic carbonate based nanocomposites for supercapacitor applications. all over Korea, there are many universities are there. If you want to doing master and PhD, first of all, you're choosing which university you want to study, and then you approaching uh, with related to your area, the corresponding professor. Uh, Especially if you want to join master program in Korea, you must be clear in TOEFL and or IELTS for the language, and also you find a university and approach it to your professor. After you getting consent from that professor, you may join uh, for the master program. The maximum duration up to 2 years, and also the funding for the master program around 4 lakh Korean won to 1.5 million Korean won. It convert into Indian money around 25,000 to 90,000 per month. And also you would like to join PhD in South Korea, there are many research field are opening for you. uh, if if you find a suitable area, and you will approach it to the corresponding professors. And also the eligibility criteria for the PhD degrees, you want to complete master degree or equivalent in the related area. And also you apply to the institution, and also you make a study plan for your research idea, and you're getting recommendation letter from your institute. And also you take your proof of nationality, and also the proficiency in English and or Korean languages. uh, the program duration around 3 years. Each semester we want to pay around 2.7 million to 4.2 million per semester. In Korean government, they providing lot of funding for PhD programs around 1 million to 2.5 million per month. Depending upon your professor and your project, they giving the scholarship. There are two semester we will joining for the PhD program. One is March, another one is September. If you want to join in March, you may applying September and November. And also you will join in September. You may applying in the month May to June. So these are the uh, PhD course of opportunities in South Korea. After you are completing your PhD, you may taking to 6 months for job searching. They providing job searching visa also. Its name is D10. So you found the job within the 6 months. Further, if you want to get in visa in Korea, you must having a valid passport and your application form, as well as passport size photo and your academic record. You must having in your bank account around your 10,000 ESD. And then the visa application charge around $60 to $90 depending upon your visa. So these are the PhD and master opportunities in Korea. If you're interesting to apply uh, for master or PhD, you may asking me after meeting. Now I come to the point. Uh, I give a brief introduction about energy, electrochemical energy storage and conversion devices. First of all, the word need for the renewable energy sources like solar, wind, and hydro, it needed energy storage devices. So the demand will creating to focusing to working on the electrochemical energy storage devices. The electrochemical energy storage devices are capacitor, supercapacitor, and battery and fuel cell is the energy conversion devices. My research area is focusing on supercapacitor. So the capacitor having high power density and battery having high energy density. So it was refilled by the supercapacitor in the term of power density as well as energy density. The following characteristics, it's showing the better and best electrochemical energy storage devices following by the characteristics: the charge and discharging time, operating temperature, capacitance, as well as power and energy density. The electrochemical energy storage devices was present here. The fuel cell is a energy conversion device. It taking similar from the electrochemical reactions, the oxidation and the reduction process. And second one is a battery. The battery will following to the redox behavior to storing the energy, which means the oxidation and the reduction process was formed by the charging and the discharging process. And third one is capacitor. We well known that the two parallel plate separated by the dielectric material, uh, after we apply the potential, it will be acting as a capacitor. The charges was accumulating on the surface of the metal plates. So the this is the capacitor. The supercapacitor is differed from the capacitor. However, here we using only metal plates, but supercapacitor we using carbon materials, which means electrode materials such as anode and cathode. So here we using dielectric in capacitor, but supercapacitor we using electrolyte. So after we applying the potential, the charge will be accumulating on the surface, uh, uh, on the surface of the electrode material, as well as the charge transfer process during by the redox process also. There are three type of supercapacitor is there. Uh,
Dear participants, please mute your audio and video mode, please.
Thank you, sir. Supercapacitor can be classified into three types. One is a pseudocapacitor, and another one is a dielectric electric double A capacitor, and third one is hybrid capacitor. The pseudocapacitor is based on the metal oxide and the polymer-based materials. It's exhibit the pseudocapacitor behavior, and the carbon-based material exhibit the electric double layer capacitance. The combination of pseudocapacitor and electric double layer capacitor to making the hybrid capacitor. The hybrid capacitor was divided into two. One is a asymmetric type, another one is composite type. The components of supercapacitor is the electrode material, separator or electrolyte, and current collectors was there. So next I would like to explain the working mechanism of pseudocapacitor. The pseudocapacitor, we having the electrode materials. The electrode materials are metal oxides or some conducting polymers was using as a electrode materials. In pseudocapacitance, there are three different types pseudocapacitance is there. One is absorbance on the surface of the metals. Second one, the intercalations, so which means redox behavior, the oxidation and the redox process during the charging and the discharging process. And the third one is intercalation process. Why during the electrochemical reactions, the charge will be intercalated to the electrode materials. So these are the three different type pseudocapacitor mechanisms. And working mechanism of hybrid type supercapacitor, the combination of electric double layer as well as the oxidation and redox process, which means paradigm process, to making this hybrid type capacitor. Here the one is the carbon material, another one is the carbon material with some metal oxides. It form like a hybrid type capacitor to make as a device. The device will be using in various electronics devices. Normally, supercapacitor was using in the various electronic materials, uh, as well as the electric vehicle, where are the high power requirement in the electric vehicle. Here they using capacitor as well as supercapacitor. In future, maybe they using in electric train as well as aerospace applications. Next, I would like to give you a small introduction about carbon material. There are various carbon materials is there, um, namely zero dimension like fullerene and aniline like carbon dots, and one day materials like carbon nanotubes, the single wall and multi-wall carbon nanotube, and the two-dimensional materials are graphene and multi-layer graphitic sheets, and then the three-dimensional materials graphene. Uh, I would like to explain a simple way. A thin rolled graphene sheet, it form like a roll. It is called carbon nanotube. It it only like a sheet. It's called graphene. So these are the difference between the graphene and the single wall carbon nanotube. Uh, and also the carbon materials was using in the various research area to making as a application in the carbon materials like a photocatalysis, drug delivery, fuel cell supercapacitor, uh, batteries, as well as the sensing applications also. It was due to um, the nature of the carbon materials. There are two Nobel Prizes for acquired from the carbon materials. One is discovery of fullerenes, and another one is a discovery of the graphene. These two materials to create the new revolution to the electronics field. The advantages of the carbon materials, we the dimension, porosity, and the novel architecture and chemical doping to the surface of uh, carbon materials, it giving the more electrochemical behavior, as well as this dimension, it may giving good electronic conductivity, and then more porosity, it's giving the easy accessible of electrolytes ions. So various electrode materials can be using in supercapacitor applications, as well as various electrolytes was using to making as a device. In my research work is based on the carbon nanotube and graphite carbonate based nanocomposites for energy storage applications. Uh, the carbon nanotube having various advantages like high stability, easy availability, and non-toxic and higher electric conductivity and good mechanical strength. It was discovered by the Ijima, is a Japanese physicist, and also he found excellent electrical conductivity as well as mechanical behavior of the CNTs. And also another one material is graphite carbonate. In this structure, it having lot of nitrogen, the nitrogen giving more benefit for the electrochemical reactions. So I can choose these two material to using as a electrode material for my applications. uh, Next, I can using some metal oxide and metal hydroxides. Due to the metal oxide and hydroxides having high specific capacitance, as well as it having huge advantages like environmental friendly, easy way to approaches, and easy way to synthesis, as well as we control the morphologies of the electrode materials. So these are the reason I choosing the metal oxide and metal hydroxides to decorating on the surface of carbon materials. So and then I can using the electrochemical studies for the CH instrument for the electrochemical analysis. These are the electrochemical setup. We using some electrolyte, uh, reference electrode as a AgCl, and counter electrode as a platinum wire, and working electrode I can fabricate it by the carbon materials. So the figure B showing the cyclic voltammetry studies of the electrode material. From this study, we can found the oxidation and the reduction behavior of the electrode material, as well as figure C showing the charging and the discharging behavior of the electrode material. Figure D showing the internal resistance as well as charge transfer resistance of the electrode material. So these are the techniques from the electrochemical analysis. So the next one is we want to fabricate the device from the cathode material and anode material uh, and electrolyte we assemble together to make as a device. The device was called the energy storage device. First of all, we want to fabricating the working electrode. If you having any anode or cathode material, adding 10% of activated carbon and 10% of binder as a PVDF, mixing together to coating on the surface of current collector. After drying, it will be acting as a working electrode for our studies. My first studies is basing on the investigation on electrochemical studies of zinc oxide incorporated functionalized carbon nanotube nanocomposites for supercapacitor devices. First of all, we having pristine carbon nanotube. The carbon nanotube was functionalized by the nitric acid from the reflux method. The functionalization process, it was modifying on the surface of carbon nanotube. It was attaching to the carboxylic acid and the surface of carbon nanotube because we want to incorporating the zinc oxide. So without functionalizations, the incorporation reaction is not occurring good. So we need to the functionalization process up to 8 hours. After the functionalized carbon nanotube was washed and dried at 80 degrees Celsius. Furthermore, we taking zinc nitrate precursor and adding NaOH at the corresponding amount. We making refluxing up to 120 degrees Celsius 3 hours after we getting the zinc oxide incorporated functionalized carbon nanotube. The respective chemicals are present here. The powder hexaide diffraction analysis, it's confirmed the crystallinity of the zinc oxide and uh, zinc oxide incorporated carbon nanotube nanocomposites. Figure E is a pristine carbon nanotube and figure D is a functionalized carbon nanotube. The structure was modified by the functionalization process, and also the respective planes 100 and 002 and 101 was exactly matching on the JCPDS card number 792205. It is formed like a hexagonal structured zinc oxide, and also the figure B is a zinc oxide incorporated functionalized carbon nanotube. And also we calculate the crystallite size around 230 nanometer by using D by Square formula. The Raman spectroscopic analysis, it's confirmed the D band and G band vibrations of the functionalized carbon nanotube as well as zinc oxide incorporated carbon nanotube nanocomposites. The as per the observation, the zinc oxide incorporated carbon nanotube, the peak intensity was suppressed from figure A. It was due to the zinc oxide was attached to the surface of functionalized carbon nanotube. The intensity was decreased. As well as the FTR analysis, it's confirmed the functionalization process of the carbon nanotube, which means the OH was attaching to the surface of carbon. So it was confirmed from the FTR analysis. Here the metal zinc and oxygen vibrations was present here. It was confirmed the zinc and oxygen was present in the composite. The scanning electron microscopic images, it's clearly showing the morphology of functionalized carbon nanotube, and figure 2 is a zinc oxide incorporated carbon nanotube nanocomposites. The zinc oxide was forming like a rod-like structure, and also it was flattened to the surface of the CNT. So further, it was confirmed from the TM analysis. The CNT was attached to the surface of zinc oxide, and also we confirming the various elements such as carbon, oxygen, and zinc was present in the composite. Furthermore, we confirming the electrochemical analysis of each materials. The figure A is a zinc oxide incorporated carbon nanotube, and figure B is a functionalized carbon nanotube, and C is a pristine zinc oxide. Compared to these three, the zinc oxide incorporated carbon nanotube exhibit the high electrochemical performance. It was observed from the specific capacitance analysis. The zinc oxide incorporated carbon nanotube exhibit the specific capacitance up to 189 farad per gram at the scan rate of 1 millivolt per second. And the galvanostatic charge discharge analysis, it confirming the charging and the discharging behavior of the electrode material. Figure B showing the pure ZNO and pure carbon nanotube, and zinc oxide incorporated carbon nanotube exhibiting high charging and discharging compared to these two. So it will be enhancing the electrochemical performance by the zinc oxide incorporation. So the specific capacitance was calculated from the charging and the discharging behavior. It exhibiting around above 90 farad per gram. And also we studying the cyclic stability of the electrode material. It exhibiting 96% retention up to 1000 cycles. The electrochemical impedance analysis, it's giving the information about the before and after 1000 cycles of the zinc oxide incorporated carbon nanotube nanocomposites. Before 1000 cycles, the internal resistance of the electrode materials was very less. After 1000 cycle, the internal resistance was increased due to the charging and discharging. It the stability will be slowly loosened by the charging and discharging process. Finally, I summarize the results of this work. The zinc oxide nanorods was grafted on the surface of functionalized carbon nanotube from the chemical reflex method, and the various characterization it's confirmed the forming like a zinc oxide was incorporated to the surface of functionalized carbon nanotube, and also the specific capacitance was calculated around 189 farad per gram at the scan rate of 1 millivolt per second. And then after 1000 cycles, the electrode exhibit 96% retention. In this work published in Physica B Condensed Matter. My second work is based on investigation on electrochemical performance of asymmetrical supercapacitor made of manganese oxide incorporated carbon nanotube nanocomposite and zinc oxide incorporated carbon nanotube nanocomposites. We following similar method to functionalizing the carbon nanotube, and also the manganese the respect amount of precursor to take to synthesize the manganese oxide incorporated carbon nanotube nanocomposites. The respective chemicals was present here. The powder XRD analysis, it confirmed the manganese oxide was formed on the functionalized carbon nanotubes. Further, the JCPDS card number 800382, it's confirmed the MN3O4 structure, as well as we calculate the crystallite size around 32 nanometer from the powder XRD analysis. From the Raman spectroscopic analysis, we found the D band and G band vibrations of the functionalized carbon nanotube as well as the manganese oxide incorporated carbon nanotube nanocomposites. It taking high crystallinity, it represents by the ID by Ig ratio. Further, the manganese and oxygen vibrations in the fingerprint regions. Furthermore, the surface was analyzed from the manganese oxide figure, and A and B showing the pure manganese oxide, and figure C and D showing the manganese oxide incorporated carbon nanotube nanocomposites. It's showing the transition electron microscopic images. It's clearly showing the CNT was present here, and also the manganese was attaching to the surface of carbon nanotube. Furthermore, the elemental was analyzed from the EDS analysis. The pristine one, the manganese oxygen was present here, and the manganese oxide incorporated carbon nanotube nanocomposites. We having carbon, manganese, and oxygen elemental was present. Furthermore, we analyzing the 3 electrode analysis of the each electrode material, and figure A is a pure carbon nanotube, and figure B is a functionalized carbon nanotube, and figure C is a pure manganese oxide, and figure D is a manganese oxide incorporated carbon nanotube nanocomposites. Compared to these 3, the manganese oxide incorporated carbon nanotube nanocomposites exhibit this large CV curve area. It represents the combination of manganese oxide and the functionalized CNT. It enhancing the electrochemical reactions from the sodium sulfate electrolytes. And the galvanostatic charge discharge analysis, it giving the charging and discharging behavior of the pure carbon nanotube and functionalized carbon nanotube, and the manganese oxide. The figure D is a manganese oxide incorporated carbon nanotube exhibit the large charging and high discharging time. It must be very useful for making as a electrode material as a device. So the comparison of the pristine carbon nanotube and functionalized carbon nanotube, manganese oxide, it taking very less compared to the manganese oxide incorporated carbon nanotube nanocomposites. It's similar from the charge discharge analysis. After calculation of a specific capacitance, the manganese oxide incorporated functionalized carbon nanotube exhibiting the 499 farad per gram at the current density of 0.1 ampere per gram. The electrochemical impedance spectrum, it's showing the internal resistance as well as charge transfer resistance of the electrode. After we checking the cyclic stability of the manganese oxide incorporated carbon nanotube nanocomposites, it was exhibiting around 75% of retention after 1000 cycle. Furthermore, we developing the zinc oxide incorporated functionalized carbon nanotube as an anode material, and manganese oxide incorporated carbon nanotube as a cathode material, and PVP and sodium sulfate based electrolyte was using as the separator, assembled together to make as a device. The device exhibiting the potential window up to 1.8 voltage, as well as it was confirmed from the charging and the discharging of the device around 1.8 volt. After we measure the specific capacitance of the device, it taking around 6 farad per gram. After 10,000 cycle, it was decreasing around 3.5 farad per gram. So before and after 10,000 cycle, initially it taking very less internal resistance. After 10,000 cycle, the internal resistance was increased as well as the charge transfer resistance was increased. After we calculating the specific capacitance of various current densities, it exhibiting 4 ampere per gram at the specific capacitance up to 10 farad per gram. And also I calculate the power density and energy density of the device. The device exhibit the maximum power density up to 2200 watt per kg, and the energy density 1.1 watt hour per kg. Finally, I summarize the results. The manganese oxide incorporated carbon nanotube was successfully synthesized from simple chemical reflux method, and the various characterization it confirmed the presence of the compound, and various electrochemical studies it may giving the behavior of the electrode material. We calculate the specific capacitance up to 499 farad per gram, and also we fabricating asymmetric supercapacitor device. The device exhibiting the maximum power density up to 2200 watt per kg. This work published in Superlattices and Microstructure. My third work is based on the investigation and fabrication of nickel hydroxide encapsulated carbon nanotube nanocomposites for hybrid electrochemical supercapacitor. The similar method to synthesizing the nickel hydroxide incorporated functionalized carbon nanotube nanocomposite. The crystalline structure of the nickel hydroxide was present here. The figure B is a nickel hydroxide incorporated functionalized carbon nanotube. It was matching on the GCPDS card number 140117, and the average crystallite size was calculated up to 20 nanometer, and also we found the various vibrations from the FTR analysis. Here, the fingerprint region, we found the nickel and oxygen vibrations in the range of 515 and 460 centimeter inverse. The Raman spectroscopic analysis, it's giving the D band and G band vibrations of the functionalized carbon nanotube and nickel hydroxide incorporated carbon nanotube nanocomposites. Here, we found the ID by IG ratio around 1.6, it taking lot of defect on the surface of carbon nanotube, which due to the addition of nickel hydroxide. And the SEM analysis, it's clearly showing the morphology of carbon nanotube, and the small particle, it's showing the nickel hydroxide on the surface. Here, the transmission electron microscopic, it's clearly showing the figure B is a carbon nanotube, and figure A is a nickel hydroxide incorporated carbon nanotube nanocomposites. It clearly showing the it was covered by the carbon nanotube, as well as it was attaching to the nickel hydroxide, and the elemental analysis, it's confirmed the presenting elemental or carbon, oxygen, and nickel was present here. The electrochemical analysis of uh, um, uh, pure carbon nanotube and functionalized carbon nanotube and nickel hydroxide incorporated carbon nanotube was present here. Compared to these three, the nickel hydroxide incorporated functionalized carbon nanotube exhibit the high specific capacitance. The specific capacitance up to 876 farad per gram at the scan rate of 0.5 millivolt per second. While the electrochemical reactions, the nickel hydroxide will be forming like a OH, and it was forming nickel oxygen hydroxide, and to losing as a one electron, the process will be reversible, so it taking electron transfer process. And galvanostatic charge discharge analysis, it's showing the figure A is a pure carbon nanotube, and figure B is a functionalized carbon nanotube, and C is a nickel hydroxide incorporated functionalized carbon nanotube. Similarly, it was confirmed by the CV as well as GCD having high specific capacitance from the nickel hydroxide incorporated carbon nanotube. So further, we studying the cyclic stability of the electrode material, it giving around 67% retention of the electrode material. So here we presents the pure carbon nanotube and functionalized carbon nanotube and nickel hydroxide incorporated carbon nanotube nanocomposites. The nickel hydroxide incorporated sample having high capacitive behavior. Furthermore, we fabricating asymmetric supercapacitor devices from the functionalized carbon nanotube as an anode material and nickel hydroxide incorporated carbon nanotube as a cathode material, and PVA KOH based electrolyte was assembled together to make as a device. The device giving the potential window up to 0 to 1.2 volt, as well as it was confirmed by the galvanostatic charge discharge analysis. The specific capacitance was calculated around 65 farad per gram uh, at the scan rate at the current density 1 ampere per gram. So further, here I comparing the functionalized carbon nanotube and the nickel hydroxide incorporated carbon nanotube assembled together to make us a device. The device exhibiting large potential window from the cyclic voltammetry as well as galvanostatic charge discharge analysis. So the device, we studying the cyclic stability. Initially, the device having 31.9 farad per gram. After 1000 cycle, it taking 23.8 farad per gram. So uh, from the electrochemical impedance spectroscopy, it's showing the before and after cycle it losing its capacitance. The cyclic stability retention up to 75% was calculated. Furthermore, we calculate the power density and energy density of the fabricated device. The device exhibit high power density up to 12,000 watt per kg, and also we calculate the energy density maximum 13 watt hour per kg. So finally, I summarize the results. The nickel hydroxide incorporated carbon nanotube was synthesized from simple chemical reflux method, and also various characterization it confirmed they formed composites. And also we calculating the specific capacitance up to 876 farad per gram at the scan rate of 0.5 millivolt per second. Further, the asymmetric supercapacitor exhibiting high power density up to 12,000 watt per kg, and also we calculating the specific capacitance of the device, it exhibiting 65 farad per gram at the scan rate at the current density of 1 ampere per gram. This work published in Journal of Energy Storage. My fourth work is based on investigation and effect of graphitic carbonated loading on the surface of titanium dioxide nanocomposites for supercapacitor applications. First of all, we want to synthesizing the graphitic carbonated from urea. 50 gram urea I take to take the 250 ml alumina crucible, and it was covered by the alumina foil. Further, I kept in furnace up to 600 degrees Celsius. Uh, After the graphitic carbonated was synthesized from the uh, self-supporting atmosphere. So furthermore, the graphitic carbonated and the pure titanium dioxide nanoparticle was using to by the mechanochemical method. After 600 degrees Celsius, we using for the thermal spreading method. Finally, we synthesizing the graphitic carbonated and the titanium dioxide based nanocomposites for the energy storage applications. Here, the titanium dioxide weight was fixing, and only we changing the graphitic carbonated weights at the various loadings. The powder XRD analysis, it confirmed the crystallinity of the titanium dioxide as well as the graphitic carbonated 002 planes. Here, the increasing loading amount, the graphitic nitrate, the carbon peaks was raised from the XRD analysis. We calculating the average crystallite size of the titanium dioxide nanoparticle, it around 556 nanometer. Furthermore, we studying the FTR analysis of the prepared composites. It taking various carbon nitrogen vibrations, single carbon nitrogen double bond and carbon nitrogen single bond vibrations is there. It confirm the it forming like a graphitic carbonated, and also the Raman spectroscopic analysis. The low loading sample it's showing the titanium dioxide peak, and after the higher loading, the peak will be disappear. It was due to the covering of graphitic carbohydrate on the surface of titanium dioxide. So the scanning electron microscopic images was present here. Figure A and B is a pure graphitic carbohydrate. The graphitic carbohydrate forming like a sheet-like structure, and also the various loading was present here. At the higher loading, the graphitic carbohydrate and the titanium dioxide was present here. In TEM analysis, it clearly showing the sheet-like structure is graphitic carbohydrate, and the particle, the big size particle was present here, and also the graphitic carbohydrate was covered on the surface of titanium dioxide. So the EDS elemental conformation was present here. The presenting elemental are carbon, nitrogen, oxygen, and titanium dioxide. Titanium was present here. So furthermore, we studying the electrochemical analysis of the um, various electrode materials. Figure A is a very low loading sample. Figure B is a 20%, and figure C is a 33%, and figure D is a 50%. Compared to these four, the 33 loaded sample exhibiting good electrochemical performance compared to all other. And also it was reflected from the galvanostatic charge discharge analysis. The 33% loaded sample exhibiting the large discharging and charging and discharging time compared to all other. So further, we calculating the specific capacitance of various sample. The 33 weight percentage loaded sample exhibiting around 864 farad per gram, and also it was confirmed by the galvanostatic charge discharge analysis. The 33 weight percentage loaded sample exhibited the high specific capacitance. Furthermore, we studying the electrochemical impedance spectrum of the various sample. The 33 weight percentage loaded sample exhibited the low internal resistance as well as low charge transfer resistance. The cyclic stability of the electrode materials was studied up to 2000 cycle. It was exhibiting around 70% retention. So the Coulombic efficiency was calculated. It was exhibiting around 70%. Furthermore, the elemental weight percentage in EDS and nominal loading of the graphitic carbohydrate was present here. Here, the 1 point at the 33 weight percentage loaded sample exhibiting the combination of nitrogen was present, titanium and nitrogen was present here. It may giving the better performance from the electrochemical analysis. Finally, I summarize of my research work from these studies. The graphitic carbohydrate and the titanium dioxide based composite was synthesized from thermal spreading method and various characterization. It confirmed the crystalline and spectroscopic and morphological and elemental analysis of the present compound. And also we calculating the specific capacitance of the electrode materials around 864 farad per gram at the scan rate of 1 millivolt per second. After we studying the cyclic stability of the electrode material, it exhibiting 70% of retention. In this work published in Material Science in Semiconductor Processing. My fifth work is based on investigation on titanium dioxide supported silver graphitic carbohydrate ternary nanocomposite for electrochemical applications. This ternary nanocomposite was synthesized from two different samples. One is a CAT, which means titanium dioxide on the surface of silver nanoparticle, and then we adding graphitic carbohydrate sheets on the surface of this silver loading titanium. So second one is the titanium surface was covered by the graphitic carbohydrate, and after we adding silver nanoparticles on the surface of graphite carbonate. So here we fixing the uh, titanium dioxide and graphite carbonate. Only we changing the silver weight percentage to the surface of these samples. The powder XRD analysis, it's confirmed the crystallinity of titanium dioxide nanoparticle, and the FDR confirmed the functional group vibrations and nitrogen vibrations was present in the range, as well as uh, it's showing the stretching modes of the triazine derivatives, because the graphite carbonate is a layer type material, so it giving the triazine vibrations. The transmission electron microscopic images, it's clearly showing the bigger size particle is a titanium dioxide, and very smaller size particle is a silver nanoparticle, and the layer is uh, uh, a graphite carbonate based material. In this work, the silver was on the surface of graphite carbonate, and this figure it's clearly showing the titanium dioxide was present here, and silver nanoparticle was inside to the graphite carbonate. So these are it was confirmed from the TM analysis. So further, we confirming the elemental in EDS analysis. The elemental are carbon, nitrogen, oxygen, silver, and titanium was present in the composite in the CAT and ACT samples. Furthermore, we studying the electrochemical behavior of the various samples. Here, here we changing the weight or loading 80 to 16 percentage. Here the ACT 16 sample, uh, it's showing the better electrochemical performance compared to all other sample. It was reflected from the galvanostatic charge discharge analysis. The ACT 16 sample, it's showing a high charging and discharging behavior of the electrode material compared to all other. So further, we calculating the specific capacitance of all material. ACT 16 exhibiting large specific capacitance compared to all other. It was confirmed by the galvanostatic charge discharge analysis. Um, the sample ACT 16 sample exhibit high specific capacitance up to 410 farad per gram. After we studying the coulombic efficiency of the electrode material, the electrode was exhibiting around 90% coulombic efficiency after 5,000 cycles. So finally, I summarize the results. The ternary nanocomposite was synthesized from simple chemical impregnation method and thermal spreading method, and we found ACT 16 sample it exhibiting good electrochemical performance. After uh, the cyclic stability, it taking around 90% coulombic efficiency after 5,000 cycle. In this work recently accepted in electronic material letters. Finally, I would like to thank my supervisor, Dr. M. Krishnakumar sir, and my co-supervisor, Dr. N. Alamuthu sir, and my mentor, Dr. P. Devendran sir, and co-mentor, Dr. P. Lakshmanan sir. Thank you very much. Thank you, sir. Give me a wonderful opportunity to present my research work in front of faculty members. Thank you, sir. If you have any question, please ask me, sir.
Dear participants, if you have any question, please ask to our sir.
Dear sir, good evening, sir. It's a nice presentation, excellent and informative, so highly informative. Really,
Thank you,
it's
sir.
wonderful work, sir.
Thank you, sir.
I'm Kanak Sabhavati from Rajesh College itself. And please clarify which electrolyte was used in this GCD, sir, because I didn't mention about that electrolyte. Which electrolyte is used in the GCD studies, and also the PVA separator. You are used PVA as a separator.
Oh, yes, sir.
Yeah, in that case, also you have used some electrolyte. Which
Yes,
electrolyte
yes.
is used in that?
Normally, we using KOH and sodium sulfate based electrolytes, sir. If you're having 1 minute, sir.
Dr. Ranjit sir,
Yes, sir.
Dr. M. Kanasavadi from Chemistry Department is a leading researcher of our college, sir.
Oh, okay, sir. Okay, sir.
He is an expert in electrochemistry.
Oh,
And
okay, sir.
he has done his PhD work in Central Electrochemical Research Institute, Sikri, Karaikudi, sir.
Okay, sir. Okay, sir. Okay, sir.
Okay, yes, yeah.
Okay, sir. Here, in this work, 1 minute, sir. You're asking PVP based work, sir?
Yeah, yes, sir. Yes, sir. Yes, sir.
PVP or PVA, sir?
PVA, sir. PVA, polyvinyl acetate.
Okay, sir. Yes, sir. Here we following PVA and the Q, which we taking 8:1 ratio, sir. It forming like a semi-solid, sir, and it was using as a electrolyte for making as a device, sir. Here, what is your question, sir?
Regarding that electrolyte, in GCD also you have used directly KOH as electrolyte or sodium sulfate as electrolyte, isn't it, sir?
Oh, in this work is separate, sir. In this work, we using only KOH, sir. So KOH and PVA we making as a gel electrolyte, sir.
Okay, sir. Good. Thank you, sir. Thank you. And among you have compared nickel hydroxide, manganese oxide, and all those things.
Yes.
Is it these nitrates are having better specific capacitance compared with others, isn't it, sir? Compared with nitrates, the specific capacitance is relatively higher for nitrate-based materials than the
Yes.
oxides or hydroxides. Am I right?
Yes, sir. Yes, sir. The specific capacitance was based on we calculating using potential window as well as time and mass of the electrode materials. In this carbon-based work, it was taking large potential window compared to graphite carbonated works. So it taking the specific capacitance was less compared to that one. But in this case, nickel hydroxide incorporated functionalized carbon nanotube, it taking higher specific capacitance, sir, compared to carbonated work, sir.
Okay, sir. Thank you. Thank you, sir. It's excellent work, sir. Thank you very much, sir. Thank you.
Thank you very much, sir. Thank you, sir.
Hello, sir.
Yes, ma'am.
Sir, actually, I could understand what is meant by functionalized carbon. Can you please differentiate what is the difference between activated carbon and a functionalized carbon?
Okay, ma'am.
Yeah.
Okay, ma'am.
Yeah.
Madam, please introduce yourself, ma'am, please.
Sir, I'm Dr. Sasirega from Avinaslingam University, Coimbatore.
Okay, ma'am. Okay, ma'am. Thank you, ma'am. The functionalized carbon nanotube, we modify the surface of carbon nanotube because the pristine carbon nanotube, if you using directly some other loading on the materials to the surface of carbon nanotube, it cannot be attaching. It cannot be attaching good way because there is no vacancy to attaching to the surface. But if you do functionalization process, it may having carboxylic group acids. So if you having some metals, it can be easily attaching to the surface of carbon nanotube. This is the advantage of functionalization process, ma'am.
Yes, sir.
The activation carbon, if you want to take activation process, normally some people they using KOH was using to activating on the surface of carbon nanotube in the way of they using furnace, and they maintaining 800 degrees Celsius to creating more pores on the surface of tube. So it means they activating on the surface of tubes, ma'am.
Yes, sir. Thank you, sir.
Thank you,
very
ma'am.
much, sir. Yours is a very excellent presentation. It was very useful. Thank you, sir. Thank you so much.
Thank you, ma'am.
Okay.
Hello, sir.
Yes, ma'am.
Hello, sir.
Yes, ma'am.
Sir, it's audible, sir.
Yes, ma'am. Audible, ma'am.
Yes, sir. Yes, sir. It's a very wonderful presentation, sir. So,
Thank you, ma'am.
my question is, yes, yes, sir. Basically, I'm working in the field of gas sensor.
Okay, ma'am.
So, my question is, how far this carbon-based material is suitable for gas sensing applications?
Uh, I'm not relating in more gas sensor, ma'am. So normally
Yes,
carbon
sir.
material, you may modifying to the surface, ma'am, with the functionalization process. If you doping some elements like nitrogen, sulfur, or phosphorus on carbon materials, it giving additional electrochemical performance. In the case of if you're making gas sensor, you find suitable elements to doping to the surface of carbon material, and you can use to your application, ma'am.
Okay, sir. One more question. Sir,
Yes, ma'am.
your work is fully based on electrochemical workstation, right, sir?
Yes, ma'am. Yes, ma'am.
Electrochemical, sir. If we carry over our work in sensing related work in electrochemical workstation, is it called as a electronic tank? Because in sensors, gas sensing materials we are developing means it's a electronic node. The similar
Okay,
way
ma'am.
we are performing the experiments, or we are developing a sensor using electrochemical workstation, whether it is called as a electronic tank.
Oh, normally some people's doing electrochemical sensors. They detecting uh, what I'm saying, pesticides or some toxic elements. In the way they using electrochemical sensor, ma'am. But your cases, it's gas sensor. It's totally different from the electrochemical sensors. Uh, um, I'm not more knowledge in gas sensor, ma'am. I'm not having any idea, ma'am.
Ma'am, please introduce yourself.
Okay, sir.
Uh,
Sir, I'm Dr. R. Pandishwari from Sri Ramakrishna Engineering College, sir.
okay, ma'am.
Then
If you
one more,
okay, ma'am. Okay,
uh,
ma'am. You asking, ma'am.
one. Yes, sir. Sir, is it possible to detect the heavy metal ions using electrochemical workstation, sir?
Oh, yes, ma'am.
Because
Yes, ma'am. Yes, ma'am. If possible, any metals you have, uh, you can detect in electrochemical methods. If you if you making um if you making buffer solution, ma'am, and then you inject uh, your sample, which means your heavy metals to the buffer solution, and you can run the instrument. You will find before and uh, after taking results, it will be detecting on electrochemical reactions on the oxidation and the reduction process by your heavy metals, ma'am. So it's possible to detect heavy metals in electrochemical uh, workstation, ma'am.
okay, thank you so much, sir. Thank you for answering all my questions. Thank you.
Thank you, ma'am. If can I suggest to some work to your gas sensing application, ma'am? If you want to make a best gas sensor materials, you may find suitable uh, um, carbon materials with some metals. They can easily detect some gases. So which gas you want to find, you found the suitable element, ma'am, which means metallic state. it can be easily oxidizing from that gas. So you will found the suitable element, ma'am, with the addition of carbon material, ma'am.
Oh, sure, sir. Basically, I'm working fully in metal oxide based gas chemical sensors, sir. So
Okay, ma'am.
now I'm thinking about whether we are adding the metal oxides along with carbon based material means it gives some good results or some enhanced results. That's why I'm asking
Yes,
in this gas
yes,
sensor
ma'am.
related.
You will try, ma'am, without metal oxide, only metal with carbon materials. You will try, ma'am, and then maybe you getting good results, ma'am.
Yes, sir. Thank you, sir. Thank you so
Thank
much.
you, ma'am.
Excuse me, sir.
Yes, sir.
Actually, if you have been used to
Sir,
functionalize
please
CNT.
introduce yourself, please.
So, okay, I am Navanithan, sir, from JKK Nataraja College of Arts and Science. Okay,
Yes,
I have
yes,
a
sir.
query,
Yes, sir.
not a
Yes,
query,
sir.
it's a doubt.
Yes, sir.
Basically,
Okay,
you
sir.
have been used functionalized CNT, right?
Yes, sir. Yes, sir.
You have told that the reason for functionalized CNT to make the adhesions with metal oxides.
Yes, sir.
Adhesions are what is called interhalations, whatever.
Yes, sir. Maybe.
Okay. So my
Okay, sir.
doubt is basically CNT has good conductive nature.
Yes, sir. Yes, sir.
But if you make the functionalization, what would be happen? Either the conductivity can be increased or maybe reduced. That is one story. And
Okay,
another
okay.
thing is in the same questions I have another
Okay,
question
sir.
is basically for that electrochemical studies, especially for supercapacitor applications, we are simply concentrate on the ionic interactions with the electrode surface,
Okay,
right?
sir.
So in
Okay.
that case, we focused on the porosity, right? So can you correlate between the functionalizations and porosity? Because the CNT, if you functionalize, there would be a chance of increasing the defects. So at the
Yes,
time, it
yes,
may be
yes.
chance of reducing the surface porosity. So how could we manage in both things? So can you explain that one?
Okay, sir. I will try to explain, sir. In the case of functionalizations, I'm already explained. The functionalizations, it can, we want to high electrochemical performance, right? So
Yes.
we without functionalization, if you're adding some metals, it cannot be attaching well to the surface, so it cannot giving a good what I'm saying, a synergetic effect between the metal and your carbon. So after your functionalization, it will be more attaching, it making synergetic effect from the metal oxide and maybe your functionalized carbon nanotube. In the case of porosity, uh, if in the case of porosity, if you having electrolyte ion size will be playing a main role in the electrochemical performance, because you are if you're making very what I'm saying, it's a mesoporous material, it's okay. It's a if you're making like a micropores, it it making a good activity compared to mesoporous. So the electrochemical performance will be depending on uh, the pore size of the
Yes, sir.
yes, what I'm saying, the pore size of the electrode material, sir. So if the functionalization process, as per my understanding, it not uh, what I'm saying, it may it may uh, it may blocking the pores, but on another hand, it will be enhancing the electrochemical reactions also. So in the case of porosity, only ion absorption.
That's up.
But yet, yes, in the case of you adding metal on the surface, it is taking electronic transfer. Electronic transfer giving high specific capacitance compared to the absorption of ions from the pores. So this is the relation between the pores and the functionalize after functionalization to attaching the metals sir. So if you understand, sir, if you're not understanding, I will explain once again, sir.
Yes, sir, I understand. You have mentioned that synergetic effect. Right?
Yes.
In what manner you have been mentioned the synergetic effect? Either you can concentrate about any bondings or that's just interactions, force some ionic interactions.
Or if you want to
The meaning of
found the
synergetic effect.
synergetic, yes, I will explain, sir. Oh, sorry.
No problem.
Here you found this is the pristine carbon nanotube, and
Yes.
this is the functionalized carbon nanotube. Okay, sir.
Okay, sir.
After combining this the nickel hydroxide to the surface of a functionalized carbon nanotube, it reducing the charge transfer resistance, which means it taking more conductivity compared to the functionalized one, and also it creating very low internal resistances, sir.
Okay.
Thank you, participants. If you have any query, I will post his email ID. You can contact him definitely. Please kindly fill the feedback form. Thank you so much. Professor Jayalakshmi, ma'am.
Yes, sir. Good evening to all. Yes, sir.
Okay, ma'am. Can I stop the presentation, ma'am?
Yes, sir.
Sir, sir, excellent presentation, sir. Thank you, sir.
Thank you, sir.
It's time to vote of thanks. On behalf of Department of Physics, Rajbarim Raju's College, it's my pleasure to deliver the vote of thanks. At first, I would like to thank our chief guest, Dr. Ranjit Kumar Raju, who spared his busy schedule to grace this occasion. Your session is really awesome, sir, and informative for us. Thank you, sir.
Thank you.
Then I would like to thank our management principal, vice principal, and HOD for their continuous support. And I'd like to thank all the participants from various colleges and university. Finally, I thank my staff members for their endless support and friends for your cooperation in making this occasion a successful one. Thank you all. Thank you, sir. Participants, please fill the feedback form